today we'll introduce FHE on Ethereum using a coprocessor. So I will do it with Peter. We will present you everything. So the first problem on blockchain is that everything is public. So this is great. Like this is beneficial because since everything is transparent, the process is trustworthy and verifiable. However, when you want to build a decentralized application with privacy, this openness become an issue. And also we have like what we call Fully Homomorphic Encryption, or FHE. So FHE is a technology that allows a blind data process. So it means that you can process data without needing to decrypt it at any point. So if you build a decentralized application or you build like a cloud service and you use FHE, you can like maintain encryption during the whole life cycle of the data, from transmission to storage to processing. So that's why fhEVM brings a confidential smart contract on-chain using FHE. The goal of fhEVM is to bring like end-to-end encryption directly on the blockchain by encrypting inputs and states. And since everything is using FHE, you can also have a composability. So you can imagine that you have some encrypted data on contract A, encrypted data on contract B, and you can store, for example, the result on contract C. So if we think about like bring FHE on the blockchain, you can think about like many use cases with possible with that. So we can talk like quickly about like the blind auction, for example. If you think about blind auction without FHE, it would mean that any bidder will push encrypted bids on chain. But these bids at the end would be like decrypted to compare and decide which is like the winner of the auction. If you think about FHE, you can imagine that all bidders push encrypted bids, and in the end you can determine who is the winner of the auction without decrypting any bids, even the winning bids. So the only information in the end is you know the winner, but you don't know the amount of token he put in the auction. So what is great with fhEVM, it's that also it brings like everything directly in Solidity. So you write contract directly in Solidity. The goal here is to have like a library where you have like new types. So this is what we call encrypted types. So you have like encrypted booleans, obviously, but you also have encrypted integers for 4 bits, 8 bits, up to 256 bits. And these types can be used in many operators. So we have like a comparison operator, so you can compare 2 encrypted integers, for example, like equal, lower than, greater than. But you can also do arithmetic operation on these types. So you can have addition, subtraction, multiplication, and so on. A good thing also on fhEVM, like with the FHE, it's possible to generate a random number. So this is encrypted random number directly on-chain without the need of any oracle. So you can just create ciphertext containing an integer. Nobody knows what is the integer in this ciphertext until it is decrypted at some point. And the last thing, like I said at the beginning of this slide, it's that everything is in Solidity. So you can like easily use it directly with your Solidity stack you already know. And this is what we will look right now by taking, like, for example, a ERC20 transfer. So this is like basic example. And we can imagine that we write it directly in FHE. So as you can see, this is like pretty similar of what you would do with like plain text amount. But there are also a few differences. So we'll start with the first part. It's the add and sub, for example. So what happened under the hood, it's like we are using TF-HERS library. So TF-HERS library is a library handling types directly. So when you write Solidity code, under the hood, what you're doing is basically like manipulating everything with TF-HERS. And we basically, like for the add, we will have the add for the balance and the sub to the sender, where we remove the amount. Today, based on our benchmark, we are like around 2 or 3 TPS with a CPU, if we have like a node using a CPU. And when we talk about like GPU, we are like about 6 transactions per second for that. In the future, what we plan is to multiply everything by 5. So to have like something like a 30 on GPU, and even like when ASIC will be ready, we can reach something like 1,000 TPS. So this is a lot. The second part of this transfer method is this allow. So when you write ciphertext and you push ciphertext on chain, this is great because everything is encrypted, but at some point you would expect to have the possibility to decrypt some data, but you want to avoid like anyone to decrypt it. That makes sense. So the goal of this allow function is to have like an ACL contract, so access control list contract, directly on chain. And you can imagine that this access control list is like a key value store, where you say, okay, this ciphertext can be decrypted or can be processed by only this address, for example. So this is like just on-chain contract, and it will like allow or disallow contract and wallet to manipulate this ciphertext and decrypt it. So to use it, it's pretty like easy. Like you see the code, it's just saying that this ciphertext, I allow this address to use it, meaning like we can process it or decrypt it. The next part will be presented by Peter, and this is about the decryption and re-encryption.
Can you hear me? Okay. So with FHE, obviously you can do computation on data, and data remains encrypted all the time. You can do this in succession, many computations in a row. But for this to be meaningful, you have to, at some point, show the data. And that's why we have decryption and re-encryption. And let's look at how we do it. So on the fhEVM, data is encrypted under a FHE public key. But the secret key, obviously, we don't want to give it to some single party, because this party can decrypt all the data. It can do it offline, and basically there's nothing we can do about that. So our solution is to introduce the threshold key management service, or KMS for short. And what this thing basically does is we split the FHE secret key into multiple shares. And we give these shares to separate nodes. It will be best if these nodes are independent. And then we use multi-party computation to do encryption and decryption between these nodes. At no point in time the secret key is known to any single party. So basically, if there's an attacker, they have to basically corrupt multiple parties. And also, this system also supports secure FHE key generation, which means that when the FHEVM is created for the first time, for example, we will run the MPC protocol to create the key, and again, the key won't be available to any single party, even when it's created. It's interesting to note that the KMS is also a blockchain itself, and we use the blockchain because first of all, we want immutable lock of all the actions that happened on the KMS, all the decryptions or encryptions it did. And also we can use it for payments. Like operating the KMS, we want to basically for it to be paid. And because now the KMS is a blockchain and FHEVM is on a blockchain, we now need a component that allows these two blockchains to work together, and this is the gateway component that we introduce, and I will talk about it a bit later. But basically, it can read all the data needed to do a decryption or encryption. It can read the ACL from the chain, as Clément was mentioning. Also, extract proofs that the ACL is actually persisted on the blockchain. Fetch the ciphertext and pass all this information to the KMS to do a decryption or re-encryption. And for the KMS, it's a complex system, and we have a separate talk on it. So if you want to know more about it, you should listen to that talk. Let's look at decryption. So the meaning of decryption is to make a value public. So basically, you have an encrypted value, we put it on chain, and now we make it public by decrypting it. And it works in an asynchronous way, in the sense that the developer would call this function like gateway.request decryption and pass in the ciphertext in the form of a handle to this ciphertext. So the handle is a very small value that refers uniquely to a ciphertext, but not the actual ciphertext. And also callback function, and this function will be called eventually when decryption is done in a future block. In some sense, it works like an oracle. Yeah, that's decryption. And if we look at it in more detail, what happens is that when request decryption is being called, there is a decryption event D that's emitted on chain for a particular handle that is to be decrypted. And then the gateway just listens to these events on chain. And when such an event occurs, then the gateway will fetch a proof from the blockchain that this handle is to be decrypted. In practice, this proof is a Merkle storage proof from the ACL smart contract. Step 3, the gateway will go fetch the actual ciphertext from something called data availability layer. I'll talk about it. Basically, the DA is just a key value mapping from a handle to a ciphertext. So this is public, nothing special, just a persistent key value store. Can be implemented as a blockchain even. And once the gateway has this information, like the ciphertext and the proof, it can send it to the KMS to do the decryption, and the KMS will check the proof. And if it verifies, then do the decryption via MPC, sign the plain text value, and return it back to the gateway. And at that point, the gateway just calls the callback function in a separate transaction to the blockchain. Could be on Ethereum. The blockchain could be Ethereum itself. So, and here on the blockchain we can verify the signature from the KMS, and this way the application will know that the KMS actually decrypted the value and the plain text value is actually correct. So that's decryption. Re-encryption is a bit different because the main idea for encryption is to not make a value public, but to just show it to a particular user. For example, good example would be if you have an encrypted ERC20 token. I, for example, would like to see my balance, but I wouldn't want to make it public. So with the re-encryption, I can view it myself. For this to work, I can generate my own secret and public key pair. This doesn't have to be an FHE key pair. Can be any scheme. And basically, I can sign my public key and send it to the system. And the system will re-encrypt the value from the FHE encryption to my key. And this way, only I can see this value. Re-encryption happens fully off-chain. So this is the way it works is that there is a network call to the gateway. There's no transactions here, and we have there is an example here of how you can use it in JavaScript. Basically, we ship a library which makes it easy for users to send this networking request, the signatures and everything that's needed for it. And if we look at the flow itself, it starts by the user sending the request by signing their own public key for the handle, for the value that they want to decrypt. The gateway will again fetch the similar proof, storage Merkle proof. Again, step 3, fetch the actual ciphertext. And step 4, send all the data to the KMS, but this time including the public key. And now the KMS will magically transform the the value from being encrypted under FHE to the user's provided public key, but without revealing the value at any point in time. It's not decrypting and then encrypting. It's re-encryption, a special protocol where no information about the value is leaked. So no KMS node sees anything about the value. Any other node can see anything about the value. Just magically encrypted under the user's key. Also, again, signed by the KMS, and the gateway just forwards it back to the user, and the user can use their own secret key to decrypt the value, and only the user has this secret key. So that's re-encryption. And we've been working to make this the whole fhEVM run on Ethereum, not just on a native blockchain. So that's what we've been working on recently. And the way we do it is to, first of all, say we deploy, all the contracts are deployed on Ethereum on L1 without changing the compiler, without changing the tooling. The whole bytecode is on Ethereum itself. And what we do is we remove FHE computation from L1. Basically, we put it in a separate off-chain component, which we call the fhEVM coprocessor. And the way it works is that when, first of all, the coprocessor itself is also a full node, so it's executing all the blocks that happen on Ethereum. And when an FHEVM FHE operation is detected by the coprocessor, because it's doing executing all the blocks, it will also do the actual FHE computation. So to give you an example, if you, let's say, you want to do A plus B, and A plus B and A and B and encrypted values. On the coprocessor, we wouldn't do actual FHE computation. We will just fetch A and B from the DA and just produce a new result. So I'll talk about this in a bit, but the main idea is to remove FHE computation from on-chain. Data availability, I started mentioning it, is just a persistent key value store, and it's public. So it's just to map handles to ciphertexts. So yes, that's the basic idea. I'll go into more detail. And the benefits of doing it this way is that we don't have to change the blockchain. So we can do it on almost any blockchain. We can do it on Ethereum. And this makes it very easy to develop, because developers don't have to change networks, users don't have to change networks, they only interact with Ethereum, only a single endpoint. All the assets are on the L1, there's no bridging. You can easily mix and match plain text and encrypted computation. You can even compose have an encrypted smart contract and compose with existing, let's say, ERC20 tokens, USDT or whatever it is, and it will work automatically. And it also allows us to run FHE computation faster. I'll explain a bit how, by running it in parallel, like splitting, doing the FHE execution itself in parallel. And the way we do it is by something called symbolic execution. What this means is that on the L1 on Ethereum, we just do we don't do FHE computation. We just do operations symbolically on these handles, on the ciphertext handle. So the handle is a very small value, like a 32-byte value that refers to a ciphertext, and we essentially commit to the operation that has to be done on Ethereum itself. For example, if we do A plus B, what happens on L1 is that we just deterministically produce a new handle that is the result of A plus B, but without any computation. So in practice, we just basically hash A and B and produce a new handle C, which is the result. And that's all that happens on L1. It's very cheap to do it. It's almost no computation. But on the off-chain coprocessor, that's also a full node, when it sees that there is C equals A plus B, the coprocessor will actually do the FHE computation and insert, when the result is ready, insert the result under C in the DA layer. So that's how the result becomes available. And this works because it's very rare that people want to decrypt immediately after doing the execution. Most of the time, people will be doing multiple executions. Like if it's an ERC20 contract, you do many transfers and maybe at some point you want to see the value. Or if it's a blind auction, you'll be doing lots of computation on the ciphertext, and at the end, maybe you want to decrypt the winning bit. So the coprocessor will be lagging and filling in this data on its own pace. And I mentioned handles multiple times, but just to talk about it a bit more, it's just uint256 value or 32 bytes, just uniquely identifying a ciphertext. It can point to any kind of a ciphertext, could be 8-bit ciphertext, could be 64-bit ciphertext, any precision. And you can think of these handles as futures in the sense that when you do A plus B on L1, the result is a future that will eventually be resolved when the coprocessor does the computation. So it's asynchronous in some sense. We talked about what we do for results of computation, but we didn't talk about how a user can input encrypted data to the system, and we basically want to avoid people abusing the system by, for example, if I have a valid input, I don't want anyone else to take my input and use it. Maybe they'll use it, maybe they'll decrypt it. I don't want my input to be usable by anyone else, and that's why we require an additional step when you want to input ciphertext. And an example is ERC20 transfer. If the amount I want to transfer is encrypted, then I need to pass it from the outside as an input. So what I will do is I will first of all encrypt the plain text value, and additionally I will produce a zero knowledge proof of knowledge that I actually first of all know the value, that the encryption was done correctly, and that this particular ciphertext is to be used in a particular contract. I also don't want this value to be used in different contracts. So when I encrypt the value, I want to be used in this particular context, this particular contract that I'm using. So step one here is for the user to send the input, the ciphertext and the zero knowledge proof to the coprocessor. This is a normal networking call, no transaction. We have a library for that, JavaScript library, that makes it very easy to do the encryption and send the input. And the coprocessor will verify the zero knowledge proof. And if it verifies, it will first insert it into the DA layer so that it's a normal ciphertext that can be used as the other ones. And also signs the input. And the reason for signing is that when the user later uses the handle in a normal transaction, we want to make sure that the user cannot just come up with some random handle that doesn't have a ciphertext in the DA layer. So if the signature doesn't match, we will just fail on the blockchain itself. If it matches, then if it verifies, it means that the coprocessor signed this input. Yes, and there are different ways to secure the coprocessor. A simple solution could be to just use trust and run it in a central way. Maybe use reputation, like maybe a company is well reputable and users will trust it. Another way is to decentralize the coprocessor, and in this case we'll just run identical copies of the coprocessor and they can reach consensus on what the results are. Another way is to use fraud proofs, similar to optimistic rollups. In that case, everything that the coprocessor is doing is public, and also the data availability layer is also public, so anyone can verify if it's doing the right thing. And if not, a fraud proof can be submitted and maybe the coprocessor is penalized for that. We can also use like a third-party service to actively validate it. But the idea is that there are options depending on the application. And finally, so I was talking about symbolic execution, and that is very cheap. So what could happen is that a malicious actor can just create a contract that's doing a ton of symbolic execution, which is very cheap on L1. But this execution will lead to a lot of FHE computation that's expensive, and the coprocessor will not be able to keep up with that. So that's why we want to charge for FHE operations on the coprocessor. And also we want to charge because operating the coprocessor requires hardware resources. So we just have a different ways to do it. We can pay by fiat money, we can pay by the native token, we can pay by ERC20 tokens. We can also think about who pays. Like it could be the developer, could be the end user. It's just depending on the application. And yes, I think that's it on the slides, and I think now we have something interesting, a real demo.
Yeah, I'll just show that. We will. Okay, perfect. So, so a good thing is to look a little bit at some code and run it and see what's happening. So this is like a contract. I think it's big enough. Yeah? Okay. So we can take a look at one function. It's a mint. So this is like an ERC20 contract. So mint, in this case, it won't be encrypted. So this is like plain text mint amount. But as you can see, we still have some TFHE add function. So it means that even if you send a minted amount in plain text, this amount will be added to the balance of the owner of the contract. But the balance of the owner is encrypted. So what we are doing there, we are adding the minted amount to the current balance of the owner, which is like maybe not 0. So this is like a TFHE operation because you want to add plain text to an encrypted amount. Okay. So this is like the first line, and the 2 lines following are the allow we discussed earlier. So the idea is like, since we just created a new encrypted handle, so this is the result of this TFHE add will be like a new handle. We want to let this handle be accessible for the owner. So if the owner at some point want to see his balance, well, he need to access it. And also you need to give access to the contract. So this is a 2 line for the TFHE allow. So the first line would say, okay, this ciphertext can be decrypted at any point by the contract. And the second would be like the owner of the balance can at any point do a re-encryption to get his balance. Then you just add the unencrypted value to the total supply, and you just emit an event. So pretty simple on this side. So this is a mint, and we can take a look also at the transfer function. It's just there. So the transfer function is a little bit more complicated because we receive an encrypted amount. Because when you want to transfer some amount to someone, you don't want to disclose the amount. So you send an encrypted amount to someone. So the first thing is to verify that you have enough token, because if you want to transfer a large amount and you don't have enough token, this is not good. And you don't want to decrypt any balance at this point. So this is the goal of this select value, this select function, sorry. You see first line. This select is basically if the condition, so the condition is transferable. This is like computed above, just there. If this encrypted boolean is true, the value will be the second parameters. If is transferable is false, the third parameter will be set. So what we say, okay, the transfer value is the amount, or if the person has not enough fund, we'll say the transfer amount to 0. Like this, we transfer nothing, and we, in some way, cancel the transaction by just adding 0 and removing 0. Because we don't decrypt anything. This is like everything is done in an encrypted manner. So we can't have the concrete information. The only thing we can do is change the amount by 0 if something is false in this case. So then we can have like the new balance for the receiver. Yeah, the receiver. So we just add the transfer value, which is like the amount or 0, to the balance. And we directly assign the authorization for this new handle. So we let the owner of the balance to decrypt, re-encrypt the value by calling the hello, like we did for the mint. And it will be exactly the same for the second part, for the sender, where basically we do the same. We remove the transfer value and we reassign correct authorization to the owner. So this is basically this is the code. So when you have this contract, like you see, this is pure Solidity, and since we have like coprocessor on Ethereum, we can like directly deploy that on Sepolia and play with encrypted types directly on Sepolia. So this is what we will do. So we have like a small website to test that. We just deploy a contract on Sepolia. So this is like the contract we've seen. So the RC20 will be deployed and we'll start with 0 token in it. So the first thing to do is to mint it. So as you can see, like we just display the balance. So you can see the handle is 0x0. So it means that I don't have enough tokens. So for now, the handle is null. I don't have any token of any sort. But if I try to mint a few tokens. So I just pushing like a basic transaction. So it's just calling mint function. So I would expect to have an encrypted balance with the value of 1,337. And this is the case. So like you see, it's like more like instantaneous because I'm the only user right now. So we lost connection. And so as you can see, the handle changed. So now on chain, on Ethereum, on this specific contract, my balance is 0x FHEVM. So it's a UIN 256. And this is the handle of an actual ciphertext. This ciphertext is stored somewhere else on the coprocessor side, but on chain you have this handle, and you have like a DA layer, the data availability layer, where you can verify that this actual handle is this ciphertext. And if you decrypt it, because I have the right to decrypt it, I'm the owner, this is the value I get. I can also like check quickly on SRScan the transaction for mint, and since we saw that the mint is plain text, if I look at parameters, it's just like directly the amount is just 1337. I think we can see the plain text in logs. Yeah, you see the plain text there. So this is like plain text. This is what we did, but in our case, if we start playing like by transferring some tokens, so I will take the second account, for example. And if I transfer a few tokens to my second wallet, let's say this. So what you see in logs, the first thing to do is to encrypt this 337. So to do that, it will be done like client side. So no information leaked from my browser. So the value is encrypted directly in my browser. We have like some WASM to do it directly in the browser. And this value then will be sent to the coprocessor. So the coprocessor will just receive the ciphertext and the proof and returns like correct handles. So this is like a U256 representing the actual ciphertext. And what is sent, if I check on SRScan, and maybe it will take sometimes to load. What will be sent during the transfer is just like handle of the actual ciphertext. Ciphertext is already on the coprocessor because I pushed it before emitting the transfer transaction. But what has been sent from the method is this. And this is just the encrypted amount, like the handle representing the encrypted amount pushed on the coprocessor. So from anyone perspective, like there is no information leakage. You just see a transaction with some hash passing, but you don't have the cipher, you don't have the plain text value. And if I check what I have on my balance now, I have effectively just 1,000 now because I just transferred some tokens. And normally, if I switch to my second account, I should see my new value. I didn't check, sorry. And I see like the second account now has effectively the correct amount. So on Ethereum, you have everything like just handle and everything encrypted on coprocessor, but you still manipulate and do transaction only on Ethereum, and at no point you change your L1. That's all. I don't know if anyone has a question.
So regarding the usage of encrypted value, as you've shown, the handle are stored in the storage of the contract, I think. So if you want to do only memory operation, it's not possible to use it right now.
You can do. You mean like if you're not persisting the handle?
Yes.
You can do it. You basically. So I was saying that when you do an FHE operation, you basically hash the input handles to produce the result handle. So nothing prevents you from doing that. You can do a lot of.
So my other question is, how is the handle computed? Because I thought that it was based on the storage slots, but if it's not, then
no. The handle itself is only computed based on the inputs, on the input handle. So if you do, let's say, you do add and you pass in two handles, you just basically hash the handles themselves to produce. That's all you do. So you just hash the A and B. Let's say you concatenate A and it's not like that, but let's say you just concatenate A and B and you produce the result. And that's the result handle. It doesn't depend on state, only on the inputs.
Okay, so the same two input values will produce the same handle.
Yes, it's the yeah. So
if you do 1
yes.
plus 2 and I do 1 plus 2, this is the same handle at the end.
Yeah, but you would have to use the same ciphertext. So maybe if you encrypt one and I encrypt one, we wouldn't end with the same ciphertext. So, but if we manipulate the same ciphertext, obviously yes.
Okay. And also the underlying TFHE scheme is deterministic, meaning that if you do any operation on the same inputs, you get the same output all the time.
So on the practical side, when we have minted now some token that is in this smart contract, how would interoperability between existing ERC20 tokens and this kind of confidential transaction look like?
I think one project we have is to have like some wrapper around like classic ERC20. So the idea to say, okay, you have like a plain text ERC20 would say, and you just wrap this token with that. But otherwise, you are pretty limited if in the contract from the start you don't like handle TFHE and like any encrypted types.
Is there like any way for potential leakage of information? Let's say we wrap some amount of tokens, we send part of the tokens to some other address, and now this other address withdraws them, unwraps them basically. Kind of you can reconstruct then like how much initially now is on this other account, right? Yeah.
If you don't like design everything with encrypted types from the beginning, you like the risk is to leak at some point an amount. If you, for example, like try to do some swap, for example, with an encrypted ERC20 and a non-encrypted ERC20, this is like possible, but you leak some information at some point. So this is like the risk with like plain text, like because you need to take in consideration that you always need to think about like when you decrypt something, what would be happen in the end.
Okay. Yeah.
Thank you for the presentation. A question about the infrastructure that is needed. You were referring like you can now do that on Ethereum. What about if I want to do it in another layer too? Is it flexible enough, or right now is just on Ethereum?
It's flexible. You can do it on any infrastructure. We just need to agree on have a way to agree on the symbolic execution. Like if it's L2, then maybe you agree on the L2 on the symbolic execution, and then you have, I don't know, maybe it's like an L3 in some sense. The coprocessor outside of that does doing the computation.
Okay, but right now is deployed for Ethereum, if I get it right.
All right. In practice, this is just what we did for EthCC, but in practice you can do it on any chain.
Great. Thank you.
It has to be it has to be EVM right now. It has
Sorry?
to be EVM compatible.
Yeah. Great.
Okay.
On your example, I think that the inputs are UN64. Is it a limitation currently?
For now we just implemented a UN64. We plan like next quarter to have a UN256. I think it's like more related to timing and hardware we are using. Like today we know that we can use a 256, but for example for division it can take a few seconds. So regarding the block time, but on coprocessor this is not an issue, because if you want to divide 256, maybe it will take longer, but you just delay the decryption process. You can like queue many operations and maybe have wait few seconds for a specific transaction because you want to divide something bigger. So on coprocessor it's planned to have bigger types, and we are like for now we are running everything on CPU. But like running it on GPU will be like far easier to have bigger types. But it's planned next quarter. We have, for example, encrypted address, for example. So this is 160 bits already. Thank you.